All right, we're back again, lecture at 3. We're going to get into the homeostatic control of glucose. Now, what you folks are seeing here is different processes. So I want to point out absorption, getting small molecules into the bloodstream. And then from the bloodstream, we're going to now have these monomers enter cells. Okay, so I have two columns here. I have what's happening when I've fed, but I also have an excess of molecules. And then what happens when I'm in a fasted state. So whenever you're in a fed state, your body switches metabolic reactions towards anabolism, right? Because you have building materials, so we build. But if you're in a fasted state, your body starts to break down macromolecules in order for you to get those monomers to cells that need them. Now, what I want to show you folks is when we are fed, we secrete the hormone insulin, right? And insulin now allows us to get these sugars, simple sugars like glucose, into cells, right? So we can now use them as an energy source. But if we have excess sugar, right, is that what we can do now is we can now anabolically convert those sugars into a macromolecule called glycogen. And if you remember glycogen, this is a carbohydrate that humans make. We can store sugar. This is our starch, right? Now, we store glycogen or make glycogen in the liver and the skeletal muscle. Now, in the fasted state here, yes, fasted state, this is when we're hypoglycemic. And because our brain needs glucose, the hormone glucagon is secreted, which then turns on processes that allow us to break down glycogen into sugar monomers that can be released into the bloodstream so we can distribute these monomers to the cells that need it. Okay, now glucose metabolism, if you noticed, it's the only process controlled by hormones, right? And the reason is because it needs to be under tight homeostatic control. So why does glucose need to be under tight homeostatic control? Here's the reason, and let's write these reasons down. Number 1, glucose is osmotically active. What does that mean? Is because if you have too much glucose in capillaries like this, right, is water's going to come in here. And if you get too much water in a capillary, you can burst these capillaries, which now can lead to necrosis of tissue, and you don't want that, right? The second reason is it is the brain's primary energy source. Okay, so those are the reasons. All right, now as we get into the mechanisms of how we secrete insulin and glucagon and control glucose levels, we got to do a quick anatomy review. So here's a pancreas. And remember, the pancreas is both exocrine and endocrine function, right? So we're going to talk about the endocrine cells in here. And if you folks remember from anatomy, that endocrine cells are living in these structures called islets of Langerhans, right? And so they contain different cell types. And this is the cell types that I need you folks to be familiar with. Now, in the islets of Langerhans, there's 2 cell types. The first cell type that we need to know, because we're going to do some mechanisms in here, are alpha cells. Okay, so alpha cells secrete glucagon. Okay, now the second type is going to be beta cells, and beta cells secrete insulin. Now, this is physiological control now, yes? So the alpha cells and the beta cells must constantly be able to measure glucose levels in the bloodstream, is because they secrete glucagon and insulin based on glucose levels in the bloodstream. All right, let's get into the mechanisms. How do we control glucose? And so this is physiological control, okay? So we're going to utilize something called a glucostat, which means that we're going to control physiologically the amounts of glucose that are in our bloodstream. Now, we have something called antagonistic control. Here's this word again, right? Now, I'll explain this shortly, but plasma glucose levels should be around 3.9 to 5.5 millimolar per liter. You don't need to memorize this number. Later, if you folks are doing a bunch of labs, you'll memorize this when you start working. But for now, I will give you any of the values that you folks need on any exam. Now, here's our glucostat. And you folks have seen this before. Yes, midterm 1. So when glucose levels get too high in the bloodstream, insulin levels will increase, but glucagon levels will decrease. And that's what it means, right, about this antagonistic control, meaning that if one hormone is being secreted, the other hormone is not so much. Because remember, insulin and glucagon, they are two sides of the coin. They are doing opposite functions, okay? Now, after some time, insulin is being secreted. That means I am getting glucose into cells. And so, of course, plasma glucose levels are going to drop. But what happens is it starts to dip a little bit too low. And in doing so, we now shut off insulin release and we turn on glucagon release that allows us now to have an increase of glucose levels. So as you folks see here, we have our sinusoidal curve, but instead of drawing it out this way, right, is that we've drawn it in a circle. Glucostat. Okay, now here we go. Let's review. Remember, glucose in excess right here, right? Is I'm going to turn on the production and release of insulin, which is anabolic, which means I can make glycogen. And remember, if I have maxed out the storage of glycogen, so remember, glycogen can be only stored in skeletal muscle and liver in large quantities. There's only so much we can store in those cells before we start bursting cells. Do you want to burst your cells? I don't. Okay. So after we've maxed out in our space, in our real estate, we start turning glucose into fat, right? And so that's all done via insulin. Thank you, you anabolic insulin, you. Now, the opposite, okay? This is this antagonistic control. When we have glucose that is too low, we gotta use glycogen storages in order for us to get glucose. So glucagon is catabolic. I break down the bonds of glycogen in order for me to make glucose. Now, if you don't remember what glycogen is, go back to our chemistry lecture where we talk about carbohydrates. Now, the last thing, and this should tie up nicely, and this is review from different lectures, insulin secretion will be shut off when the sympathetic nervous system is turned on. And this should make sense to you because remember, what happens with sympathetic nervous system? Fight or flee, right? And so do we want to be making glycogen? No, we need to make glucose in order for us to get glucose into the bloodstream to be shunted to our skeletal muscle, right? Now, it shouldn't surprise you that the parasympathetic nervous system will turn on insulin secretion because of rest and digest, okay? When we want to digest sugars, parasympathetic nervous system will help us do that. All right, now this is all big picture stuff, okay? So let's get smaller, even tinier, right? Now let's talk about how does glucose get inside cells. And in order to go over that, I need to bring you back into time. We can get glucose into cells via the GLUT transporter. You folks remember this? Oh my goodness gracious. So remember, glucose is small and polar. Therefore, it needs assistance to get into cells. So GLUT transporters allow us to have, remember this word, facilitated diffusion. Yes, that means I can have glucose travel down its concentration gradient. Yes, let's just write that because don't be forgetting this stuff, please. Glucose travels down its concentration gradient. Now, there are 7 different types of GLUT transporters. Okay, I'm only going to ask you to know 2, just 2. Okay, and if anybody grumbles, I got a list of 7 that I'm going to have you memorize. I had to memorize 7, and I'm a little salty about it still. Now, the first one is called GLUT2. Okay, GLUT2 is a type of glucose, right? GLUT transporter that is not regulated. What does that mean? That means that it's always always on the cell membrane. Okay? Now, if one is not regulated, the other has to be what? Regulated. Okay? So this is GLUT4. This thing is regulated. Guess what it's regulated by? Regulated by insulin. Okay? So it's not always on the cell membrane. It's only exocytosed onto the cell membrane when insulin binds to its receptor. Oh, okay, that's where we're going, people. I'm excited. Okay, let us begin. All right, first, let's talk about GLUT4. Now remember, GLUT4 is regulated by insulin. Okay, so I'm going to put this textbook picture up for you folks, and what you folks are looking at is 2 scenarios. I have the fasted state and I have the fed state. All right, now what's going to happen is if I haven't eaten yet, right, I haven't stimulated insulin secretion. So right here, what you folks are seeing is this is the insulin receptor. However, I don't have insulin binding to it yet. Okay, and what you folks are seeing here is this is a secretory vesicle with GLUT4 on here already. And I drew this mechanism out for you folks in the beginning of the semester when we did our Follow the Bouncing Ball lecture. And if you folks remember, there was the second messenger in here called IRS1. Do you remember that? No? It's okay. Now, this is what's going to happen when insulin binds. Okay, so let's say that I eat, that's what it means to have fed state. I eat, I have a surge of glucose in the bloodstream and it stimulates insulin secretion. Now, insulin is going to bind to its receptor and it's going to turn on its second messengers. That it's okay that you folks don't remember IRS, but do know that this is a membrane receptor, so I'm going to have second messengers turned on. And then that's going to start a whole cascade of events that's going to allow me now to 1, let calcium enter cell. Yes, because I need calcium for exocytosis, right? So if I let calcium enter the cell, that's going to allow me to have exocytosis of GLUT4. Yay! Okay, GLUT4. And then when GLUT4 is now on the membrane, glucose can travel down its concentration gradient. Okay, does that make sense to you? Now, another thing that happens in this signal transduction cascade, all that is I'm turning on a whole bunch of second messengers inside the cell. Okay, another thing is I can turn on or upregulate transcription and translation of more GLUT. Not just GLUT. You cannot just say GLUT because now we have 2 that we need to know. You have to say GLUT4. Okay, does this make sense? Okay, majority of you folks are nodding your head. If not, you hit me up on the virtual office hours. Right now, let's move on. All right, now let's talk about GLUT2. Now, remember, GLUT2 is not regulated. Okay, it is always on the cell membrane, but it's only on special cell types. It's not on all the cells of our body, okay? GLUT4 is on majority of the cells of our body, cell types, tissue types on our body, right? But GLUT2 is only on specific cell types. So what I'm going to show you here, this is what's going on in a liver cell. So here on the picture on the left, this is the fasted state, not really, I haven't eaten yet. And so here, if you're in the fasted state, insulin is not in high levels in the bloodstream. So therefore, in here you see insulin is not binding. However, GLUT2 is present, and remember, it is always on the cell membrane. Now, in regards to the liver is important, and it's important to have GLUT2 on the liver because remember, the liver is where we are storing glycogen. Yes? Okay? And glycogen is our sugar storage. So here what's happening is if we have glycogen, right? And so glycogen is a big glucose molecule. So there's going to be a whole bunch of glucose molecules bound to each other times 1,000. I'm not going to draw 1,000 glucoses for you, but this is one glucose bound to another glucose. And so what's going to happen when we are in a fasted state and need sugar, right, is that there's going to be enzymes that are turned on in the hepatocyte to break this bond of glycogen. And in doing so, we can now have glucose, which is now going to be high in the cell, in the liver cell, travel down its concentration gradient into the bloodstream. Okay? Boom. That's why GLUT2, it's important for it to be not regulated by insulin. Okay? Now, look at the fed state, right? This is what's happening. So remember, again, go back to your functions, people, okay? The function of the liver, one of its function in regards to metabolism is to store glycogen, okay? We store that glucose for another time. So this is what happens when insulin is being secreted. Insulin will bind to its receptor. It's going to turn on a whole bunch of stuff to allow you now to have the manufacturing of something called hexokinase. Now, I don't want to let's not get too biochem, but what I want to show you folks here, okay, this is something called glucose 6-phosphate. Okay, you folks good? Now, ultimately, glucose 6-phosphate by a whole chain of biochemical reactions is ultimately going to then become glycogen. All right? And so what's happening now is if we now have enzymes that can now take the glucose coming into the liver cell, yes, because we just ate, and we can start packing it away as glycogen, I am now maintaining the glucose gradient. Because think about what's happening, people, yes? In a fed state, glucose levels outside of the cell is going to be high. And therefore, because GLUT2 is always on the membrane, glucose will always travel down its concentration gradient, okay? Now, after some time, you already know that glucose inside the liver cell, I'm going to reach an equilibrium. And if once I reach an equilibrium, even though there's still a lot of glucose to be stored, ain't no glucose coming into this cell. So I pack it away immediately and I start making glucose 6-phosphate, which will later become glycogen. So I can now remove glucose out of the area so I can maintain the gradient. And if I maintain the gradient, I can keep bringing all the glucose into the cell. We don't waste. We pack it all in because this thing is gold. We don't throw it away. All right, now let's get into the mechanism of how we secrete insulin, all right? And so the beta cells of the pancreas, yes, you have to know that, okay? Beta islet cells of the pancreas, they also have GLUT2 on the membrane. Is GLUT2 regulated? No, it is always on the membrane, all right? So here we go. This is part of the cell. I got GLUT2, it's always on the membrane. And what's going to happen now, right? In the presence of glucose, if I eat a huge meal, glucose now can just travel down its concentration gradient, okay? Now, next what's going to happen is the beta cells of the pancreas, they are going to make ATP, okay? Right? That's all for our purposes we need to know, okay? They take the glucose immediately and they hurry up and make ATP in the cell. And that allows us now to maintain the gradient so glucose can keep coming in the cell. Now, what are we going to do with this ATP? I'm so glad you asked me. This is what we're going to do. Now, there's special ATP-sensitive potassium channels in the beta cells, okay? And so what the ATP does is it comes and it binds to this ATP-sensitive potassium channel and it blocks it, okay? And when it blocks it, guess what cannot leave? Potassium. Okay, so and if you have a whole bunch of potassium, right, that can't leave the cell, it remains in the cell, it's going to cause depolarization, okay? And look, what's this gem over here? Yes, this is a voltage-gated calcium channel. And when you depolarize, you can now have the correct voltage to change the shape of this calcium channel and it opens. And why do we need calcium? For exocytosis. And in doing so, if this is a beta cell of the pancreas, its job is to make insulin. And as soon as calcium comes in, binds to the snare proteins, and then what can happen is I'm going to have exocytosis of insulin. You folks already know this mechanism. Okay, this is all old stuff. Now, here's something new. Little bit new, but a little bit old. Okay. Oh, look at this molecule. You see this beautiful molecule here? GABA. You folks already know what GABA is. Yes? GABA is a neurotransmitter that you folks learned about that does what? Inhibits. Okay? So I co-release GABA. And this is what I'm doing now with GABA. Pay attention, please. Look at what I've done. Okay? Look at the change. Look at the change of the cell. I've even highlighted it in yellow because the cell I'm going to draw looks exactly like the cell you just saw for the beta islet cell, but it's not. It's a different cell, okay? This is the alpha islet cell of the pancreas. And remember, the alpha cells, their job is to what? Secrete glucagon. But guess what? If you have high glucose levels, what's the hormone milieu? High insulin, but what? Low glucagon, okay? So during this time of high insulin, I cannot have secretion of glucagon, which would be counterproductive because they do opposite jobs, all right? So here, what's happening in this alpha cell, right, is the following. Look what GABA does. GABA has a receptor on the alpha cell of the pancreas, which is also called the alpha islet cell. Whatever you folks want to call it is fine. So when you now have GABA bind to its receptor, right, it activates its second messenger. And look, the second messenger now will do the following. It will now allow potassium to leave. So I have the efflux of potassium. And you already know what happens when positive charge races out of a cell. Hyperpolarization, okay? And if the cell membrane in here is negative, I can't open this calcium channel. Calcium cannot come in. And therefore, I can't have calcium-mediated secretion or exocytosis of glucagon. Now, I want to remind you where we are in the glucostat because it's easy to get lost when we start talking about a lot of details, right? We are in the fed state. I just showed you the mechanism of action of what happens right here. Yes? I showed you. We got glucose, comes in higher concentrations into the bloodstream, allows me to now have insulin secretion along with GABA, which is an inhibitor, right? And I showed you how now GABA inhibits glucagon secretion. Hence, low glucagon in the fed state. Okay, now let's do the fasted state next. All right, so here's a brand new slide. Now let's remind ourselves, what are we doing? Okay, let's stay focused, right? Especially when we're working with a lot of small stuff. You gotta stay focused. Here we go. This is the fasted state. I haven't really eaten, okay? Fasted state. Glucose levels are low, okay? And if glucose levels are low, I'm not gonna have high levels of secretion of insulin. Therefore, I'm not gonna have high levels of GABA. Now, in the fasted state, if I don't have insulin being secreted, I cannot co-release GABA. Therefore, what is going to happen to this GABA up here? It is going to pop off because I no longer have it. And if GABA is gone, I can't activate this second messenger. Therefore, what's going to happen? Yes, I'm going to now have potassium leave. I'm going to have depolarization. Yes, let's draw that potassium leaving. Potassium leaves, depolarization, calcium is coming in, and now I can have glucagon secretion. And now that glucagon has been secreted, it can do its job to increase glucose levels in the bloodstream. Okay, so let's look at that mechanism. Okay, here we go. Look at this drawing. Thank you, textbook. Right, so let's say that this molecule here is glucagon. And glucagon binds to a lot of different cell types that stores macromolecules, adipocytes, so on and so forth. But I'm only going to talk about liver cells. Okay. So in the liver, glucagon can bind to its membrane receptor. And if you folks remember, oh, look, this is adenylate cyclase, which means that I'm going to take an ATP molecule and I'm going to convert it into cyclic AMP. Is this ringing a bell? You blocked it out already? Don't block anything out. Soak it all in. Then I'm going to activate pKa, so on and so forth. And then pKa and some other downstream events is ultimately what I want to do is I want to activate enzymes. And then I want to start to synthesize more enzymes. What enzymes? I'm glad you asked. Great question. The enzymes I want to make here are the enzymes that facilitate something called glycogenolysis. What does this mean? Break down glycogen. Okay? Because that's what we're doing here, people. If this is the liver, I want to make sure that I get more sugar into the bloodstream. I need to run this reaction, right? If this is glycogen, which is a big macromolecule, I got to bust down some carbon-carbon bonds, right? Is because I need some enzyme, and we don't need to name the enzymes. Just we're going to call it glycogenolysis enzymes, all right? And then I have enzymes that's going to allow me to now run catabolic reactions in order for me to make glucose. And then I can release this glucose out, right? So remember, what channel is here? Sorry, I'm drawing red on red. Let me change my pen color real fast. Okay. And remember, the liver has what? What? You gotta talk louder. GLUT2, right? And so as soon as I make glucose will start traveling down its concentration gradient. And this is now how I can now have glucose go back into the bloodstream so that I am not hangry. All right. Lecturette 3, done. Next up, lecturette 4, we're going to talk about diabetes.